Hello everyone, welcome to another video from B.Sc or B.Tech. So last class we had discussions on Gauss Divergence Theorem and Stokes Theorem. Today we will discuss or we will do one problem from Gauss Divergence Theorem. See, this question is taken from July 2017 KTU question paper. Let's read this. Use divergence theorem to evaluate double integral f dot n cap ds, where f, vector f is xi plus zj plus yzk, and s is the surface of the cube, and the dimensions of cube is given here: x equal to 0, x equal to y equal to 0, y equal to 1, z equal to 0 and z equal to 1. Also verify this result by computing the surface integral over s. Okay. So as per Gauss divergence theorem, the equation is double integral f dot n cap ds is equal to triple integral del dot f dv. Okay. So we have to find this double integral. Yes, double integral is taken for the surface s, and s is our cube. Okay. So this surface integral has to be calculated, and we will get one value, and the same value should be got from this RHS section also, that is the triple integral V, where V is the volume bounded by this cube. Okay, and in that we need to integrate the divergence of this particular function f. Okay, so let's start doing it. So let's start doing the LHS section, that is the surface integral f dot n cap ds. And what is our surface? It's a cube. Okay, so let's start by drawing the cube. Let's draw a 3D coordinate system, because it's the cube given, a 3D figure, right? So this is your x axis, here goes your y, and this is your z axis. Okay, always try to mark in anti-clockwise direction. You can even start your x from here. Okay, so better start from this side and go in an anti-clockwise fashion. Okay, now let's start drawing the boundaries of cube. What's it? X equal to 0. X equal to 0 means it's the yz plane. Okay, the complete yz plane. This is your x equal to 0. And x equal to 1 means it is a plane parallel to this yz plane also, which crosses at x equal to 1. Okay, it's parallel to your yz plane and it crosses this point. Fine. So this is your x equal to 1. Now y equal to 0 means it is the xz plane, which means this plane. This is your y equal to 0, and y equal to 1 is the plane which is parallel to xz plane and which also crosses this y equal to 1. Okay, so this becomes your y equal to 1 plane. Fine. Now next set is z equal to 0. Z equal to 0 is xy plane. So here is your xy plane. So this is your z equal to 0 plane, and z equal to 1 is the plane parallel to the xy plane also, which crosses at z equal to 1. Okay. So here is the cube, and let us draw this neatly, because for a cube there are 6 boundaries, isn't it? And this is one boundary, second, third, fourth, 5 and 6 in the back and front. So let's draw this neatly. So let's start doing the integration. First of all, let us split this complete double integral S to 6 surfaces. That is, 6 boundaries are there, isn't it? So x equal to 0, let x equal to 0 be S1, and here is your S2, x equal to 1, and y equal to 0 is S3, y equal to 1 is S4, z equal to 0 is S5 and z equal to 1 is S6. Okay. So, let us split the complete double integral S to 6 surfaces. Double integral S1 f dot n cap ds plus double integral S2 f dot n cap ds plus etc. Last one will be double integral S6 f dot n cap ds. Okay. So, let us do this individually. First one is double integral. Okay, first surface is S1, and what is S1? S1 is x is equal to 0. Okay. So remember we are going to do this double integral S1 f dot n cap ds. Okay. So, what is f dot n cap? Vector f is given, which is xi plus zj plus yzk, xi plus zj plus yzk dot, and what is n cap? N cap is the unit vector which is perpendicular to the surface S1. So, here is your surface S1, which is your yz plane, and the unit vector which is perpendicular to yz plane is along the negative x direction, that is x direction is in front of the screen, and the vector perpendicular to yz plane is that way. Always remember, take the vector outside the cube. Okay. So, here the unit vector is perpendicular to yz plane, which is along negative x direction, which is unit vector along negative x direction means it is negative I cap. Remember, the unit vector along x direction is I cap, along y direction is j cap, and unit vector along z direction is k cap. Okay. So, the unit vector which is away from this positive x axis will be negative x axis or negative I cap. Okay. So, for n cap we need to substitute negative I cap. Okay. So, what is the value there? Taking the dot product, it is just need to take the components for I, that is x into negative 1, which is negative x, and let us apply this x equal to 0 value for this. So, it becomes 0. Okay. So, in total we do not have any double integral because for double integral S1 f dot n cap ds is equal to double integral S1 0 ds, which is 0. Fine. Similarly, we have to do for other surface also, that is S2. S2, let us see, S2 is the plane parallel to yz plane, or this is your plane, isn't it? Here x equal to 1. So, for S2 it is x equal to 1, and f dot n cap means xi plus zj plus yzk dot n cap. N cap is the unit vector perpendicular to this S2 surface. Okay, this is your S2 surface, and the unit vector perpendicular to S2 surface. It is along this positive x direction. So, the unit vector is simply I cap. Okay. So, here dot I cap. Solving it out, we get xi cap dot I cap, which is x itself, and x value here is 1. So, double integral S2 f dot n cap value is 1, and what is ds? ds is actually the variation of that surface. Which are the dimensions for this surface S2? Here the S2 surface varies along the y direction and the z direction. So, y direction means dy is the variation, and for z direction dz is the variation. So, we need to write dy dz. Okay. And what all are the limits? Okay. So, here you can see that the z variation, z limits must be written in the outer integral. So, z varies from, see, this is the surface, isn't it? So, z varies from z equal to 0. Here this bottom portion means it is z equal to 0, and the top portion is z equal to 1. So, upper limit or the limits for the z axis is 0 to 1, and for y axis For y axis also the variation is from y equal to 0 to y equal to 1. Okay. So, it is 0 to 1. Let's do 0 to 1 dy first. It is simply y in the limit 0 to 1 and the value is 1 minus 0, which is 1. Again, let's do the outer integration, that is 0 to 1 dz. So, it is z in the limit 0 to 1, that is 1 minus 0, it is 1 again. Okay. So, the value is 1. Okay. So, we have done for S1 and S2. Similarly, let's do for S3 and S4, later S5 and S6. Okay. So, which is the surface S3? This is your surface S3. At that plane you have y equal to 0. Okay. So, S3 y equal to 0. For that section you have f dot n cap. Substitute your f value. It is xi plus zj plus yz k dot n cap. N cap here, it is the vector, unit vector perpendicular to S3 surface. So, that will be in this direction, which is against positive y axis, or we can call it as negative j direction. Okay. So, your n cap is negative j. Doing set j dot minus j, z into negative 1 is negative z, and that is it. So, taking the double integral f dot n cap ds equal to double integral f dot n cap is negative z and which is ds, or what is the variation for that plane? Variation is along x direction and the plane has its variation along z direction also. So, we can write it as dx dz. Dx dz, and similar to the limits taken for S2, here also we have the variation from 0 to 1 and 0 to 1. So, it is, let's do the inner integral first, integral 0 to 1 negative z dx, it is negative zx in the limits 0 to 1, which is negative z itself, and outer integral 0 to 1 negative z dz. What is that? It is z square by 2, negative z square by 2 in the limits 0 to 1. So, upper limit is negative 1 by 2 minus lower limit is simply 0. So, negative half is your value for S3 surface. Fine. Now, for S4 surface, S4 is, yes, here is your S4, y equal to 1. Okay. And the unit vector perpendicular to this surface is along y direction or j cap direction. Okay. So, your n cap is j cap. Okay. And there you have y equal to 1 also. So, for S4 it is y equal to 1 and again f dot n cap is xi plus zj plus yzk dot n cap is j cap, isn't it? So, zj cap dot j cap is simply z. Okay. So, I think the integrand stays the same, isn't it? Double integral z dx dz. Yes, only there is a change in the sign. Here in the last case there was negative z and here it is positive z, and the limits is also, or the plane is having the variation in x and z direction. So, the limit is also 0 to 1. Solving it out, you will get positive half, because last case we got negative half, isn't it? And the last set is for S5 and S6. For S5, which sets the first? S5 is the bottom surface, isn't it? S5 is, here you can see that z equal to 0, yes, z equal to 0 is S5, and the vector or the unit vector perpendicular to S5 is against positive z direction, or it is negative k cap. Fine, z equal to 0 and negative k cap. Let us substitute z equal to 0, and for f dot n cap it is xi plus zj plus yz k cap dot, that was negative k cap, n cap is negative k cap, and yz into negative 1 is negative yz is your integrand. Also it's not over because see z equal to 0 there. So substituting here, minus y into 0 is 0. So that means we have no need to integrate this further. F dot n cap is simply 0. Okay. Moving on to the final surface S6, which that S6 is the surface z equal to 1. Okay. So z equal to 1, and there you can see that the vector perpendicular to z equal to 1 is k cap. Okay. So z equal to 1 and unit vector is k cap. F dot n cap is xi plus zj plus yz k, and the n cap value is positive k cap. Yz into 1 is simply yz. Again let us substitute z equal to 1 for here, that is y. Y into 1 is y. Okay, now it is double integral f dot n cap is y, and which is the variation? Variation was along, see for this plane S6, the variation is along the positive x direction and the positive y direction. So for ds we can substitute dx dy. Fine. Dx dy, and the limit stays the same, 0 to 1. Doing the inner integral, it is 0 to 1, y dx, it is yx, value is simply y, and the outer integral is integral 0 to 1, and the answer for this is y dy. So it is y square by 2 in the limits 0 to 1, we get half. Okay. Now let us collect all this integration, all this double integration starting from S1 to S6. Okay. So double integral S is equal to double integral S1, double integral S2 plus etc. till double integral S6. Okay. Let me write everything. So here are the values, adding it up we get 3 by 2. Okay. So by this the LHS part for the divergence theorem, double integral S f dot n cap ds is equal to triple integral v del dot f. The left side section is over and the value is 3 by 2. Now we have to verify this Gauss Divergence Theorem, that is we need to do this triple integral del dot f. Okay. So f is available for us and we need to take the double integral. This is your f value, and let us take divergence for this f. Del is I dou by dou x plus j dou by dou y plus k dou by dou z, and dot xi plus zj plus yz k. Taking the dot product, it is simply combining the components of I, j and k. So it is dou by dou x of x, it is 1, and dou by dou y of z, it is 0, and dou by dou z of yz, it is taking the derivative of yz with respect to z, we get y. So divergence of f is 1 plus y. Okay. Now let us substitute this value over here and let us proceed doing the RHS side or the triple integral side. Triple integral del dot f is 1 plus y, and what is dv? dv is simply the change in the variation of the cube along the dimensions x, y and z, that is dx, dy and dz. Okay. And for every variation, for every axis the variation starts from 0 to 1. Okay. Let us do it. Let us start from the inner side integral, that is integral 0 to 1, 1 plus y dx, value is 1 plus y of x in the limits 0 to 1, value is 1 plus y. Let us do the middle integral, that is 0 to 1, 1 plus y dy. Okay. So it is y plus y square by 2 in the limits 0 to 1, value is upper limit 1 plus 1 by 2 minus lower limit 0 plus 0 by 2, which is 3 by 2. And the outer integral is integral 0 to 1, this value. Okay. integral 0 to 1 3 by 2 dz, that is 3 by 2 ez in the limit 0 to 1, that is 3 by 2 minus 0, answer is 3 by 2. So that's the value got from the triple integral side. Here also we got the same value 3 by 2. Thus Gauss divergence theorem for this particular function f, vector f taken for the cube whose dimensions were given is verified. This is a very frequently asked question in many of the exams related to this vector calculus. So if you like the video, please do like, share and subscribe it. Till we meet in the next class, this is Minu signing off. Thank you and take care.